one last example. And it's a good practice on some circuits, one skills too. So these values of the inductors are unrealistically large for most circuits. But it makes a good practice problem. We've got a current source. It's increasing with time. It's linearly increasing, right? It looks like that, where this is time and this is your current. And it's being pushed through one inductor and it's being pushed to two other inductors in parallel. And the thing we want to find is the current through the 6 Henry inductor and the voltage across the parallel combination of the 12 and the 6 Henry inductor. So I want you to find 1, V of t, 2, the energy stored in the 2 Henry inductor, and 3, the current through them, assuming that I of 0 at time 0 is equal to 0 amps. In other words, this is a circuit for time greater than or equal to 0, and I just threw it together at time equal to 0, so it wasn't there before time equals 0. So let's do each of these things. Jacob, how would you, let's start off by simplifying these things. We're seeing if we can simplify them. If we simplify our 12 and our 6 in parallel, will that affect the voltage across both of them, or will we destroy it? There's no question that the 12 is in parallel with the 6. But my question is, if we simplify it, will we destroy the variable we're trying to find right now, which is V? Our first step is to find V. Don't worry about I.
No.
Correct. You're not going to destroy it. Because when you replace your, when you replace your inductor here with 12 in parallel with 6 Henrys, the voltage between these 2 points are the same as what you simplified it by, right? The in between these 2 dots are the same. But the voltage between these 2 points hasn't changed when you simplify inside the points. These 2 points are outside the places that your voltage is taken outside from where you're simplifying. So you're allowed to totally simplify the inside. And what's 12 in parallel with 6? The slow way to do it is to say 12 in parallel with 6 is equal to 1 over 6 plus 1 over 12. You need a calculator for that. You can't do it in your head. A slightly faster way to do it, a much faster way, is to do this. It's 4. Here's a faster way yet. I'll show you how you can do this in your head, and it's trivial. All right. Ready for this one?
Mm-hmm.
All right. Instead of doing it with inductors, just because you've seen resistors before, I'm going to give the exact same problem, but with 2 resistors, only because you've seen it. These guys are multiples of each other. Whenever you see multiples of resistances in parallel, there's a shortcut you can do. Jacob, does putting things in parallel make the resistance bigger or smaller?
Makes it smaller.
Right. So if you wanted to create the smaller one, you could do it out of a multiple of bigger ones. In your head, can you see how 2 12s? Can you see how? Whoops. Can you put mute on just for now, Jacob, since you've got the stuff in the back? All right. In your head, you should be able to see how 2 12s make a 6. In general, if you have n identical resistors, they'll make whatever that resistance is divided by n. I mean, the intuition thing is saying, let's say that the resistance is a doorway. Opening up n parallel doorways in parallel should decrease the resistance by a factor of n. So since these are multiples of each other, make the smaller one out of a multiple of the bigger ones. That's 2 12s. Since you've got 3 12 ohm resistors, you can see the equivalent resistance is just 12 over 3, which is 4. All right, so you did it right. In our case, it's 4 henries. So now we can rewrite this. We've got our 2T current source, 2 henries up here. We've got 4 henries over here. And we want to find what this voltage is. That's our first step. So what rule will you use for it?
Like what formula?
What formula? Yeah.
Well, we know current. So V equals L I prime.
Good. Do you know the current through it? You know L is 4 henries, but do you know the current through it?
Not necessarily, but could you take that 2 Henry inductor and short it?
Nope, because you're not in DC steady state.
Oh, okay.
Things are changing.
So,
This thing is changing. This thing has a graph that looks like this over here, not constant. So let me go back to my first question, though. Do you know the current through the 4 Henry? You know the current over here, set by the current source, 2T. Where does that current flow? Let me start it off for you. Starts up flowing up here, and then keeps flowing here, and then don't leave me hanging. Keeps going through here, and then it's got to go through here, and then
goes through the 4.
It's got to go through. It's got nowhere else to go, right? It doesn't. There's no branches in it, and then it's got to go through here, and it completes its loop. So all the current has to go through here. So if you know what the current is over here, do you know what the current is right here? Through that wire?
Yes. Yes.
Do you know what the current is through this wire?
Yes. So the inductor doesn't change the.
Not if it's in series. It can't.
Okay. Okay.
I don't care what
keep it
component.
Constant.
I don't care what component you have in here. You could put my dog in series with it. And if 2 amps is flowing, 2T is flowing into my dog, 2T has to be flowing out of my dog. It's got no choice.
Okay.
If it's just a single wire going in and a single wire going out of my dog. She's a cute little thing. She's a 15-year-old pug. She probably wouldn't even feel it. All right. So what's the derivative of the current going through that?
2.
2. So therefore 8 volts. And that's the answer to the first question. Now that we've got the answer to the first question, let's get the answer to the second question. What is the energy in the 2 Henry inductor? What's the formula for energy for an inductor?
1/2 inductance current squared times 2 current squared.
Okay. So do you know all those things? You know the inductance. I said through the 2 Henry, so that's got to be 2.
And we know the current.
It's got to be 2T. So you'll square that. Now you've got 1/2 times 2 is 1. And then 2T squared would be 4T squared. And what are the units in that? What's the units of energy?
Joules.
Joules. All right. We got 1. We've got 2. It's slightly bad board technique to go backwards. But rather than starting a whole new board, let's just do it. We want to find I of t. Is I of t the same as this I of t? Here's our I of t defined. Is that the same thing as this I of t?
Yes.
Because we've simplified them, right? It has to be. Leading you down a bad path. No, it's not. Here's why. Let's do this just like we circled this I here. Let's see where this 2T goes.
Is that because in the formula it takes 1 over the inductance, so the inductance matters?
It's because this current breaks in our original circuit. Do you see how I'm drawing the pathway of the current?
Yes, sir.
So here it's 2T amps. Here it's 2T amps. Down here it's 2T amps. But here it breaks. Some of it flows on the right side, some of it flows on the left side.
Right. So you have two different current values.
Right. And so
Okay.
it's not, you can't
Right.
go to the simplified version. You got to go back to the original version. We cannot say that I of t equals 2T because different pathways. We can say that this current plus this current is equal to 2T, but we can't break it apart. So we're going to have to do something else. What's something else we can do? If it was resistances, it would be pretty easy, right? You'd find, if I asked you the equivalent for, let's say it's 2 amps. How would you solve this? Call it 2 ohms and 12 ohms and 6 ohms. How would you solve for the current through this leg? There's a rule you'd use. You'd say by inspection, this 2 ohm source doesn't matter because 2 in, 2 amps in, 2 amps out. So you know 2 amps goes in here and it gets divided. Some of it goes through this resistor and some of it goes through this resistor. So what, before it combines and comes back. So what rule is it that you use? What's the equation? What's the equation called? The rule used when you've got current that divides through 2 pathways.
Current divider?
A current divider, yeah. And so you'd remember that that this I through 6 ohms
right.
is equal to the I total times the other resistor in the numerator with the sum of the resistors in the denominator.
It's coming back.
And that's yeah, it is. And this would be the solution. So it'd be 2 times 12 over 18. So that's 24 over 18. And you divide both sides by 6 to get 4/3 amps. Unfortunately, you do not want to have to memorize new rules for current dividers and voltage dividers and new rules for meshes and nodal and all these other things you learned in circuits 1. You just want to go back to the basics and figure it out for yourself. And you can do that. Do you know, going back up here, do you know the voltage across this 6 Henry?
Yes.
Yes, you already figured it out.
It's 8
What
volts.
is it equal to? The voltage across the 6 Henry is equal to a constant 8 volts. So now, can you tell me what the current is through the 6 Henry? What is the relationship? If you know the voltage, you can always find the current.
So
just give me the formula.
Yeah. Okay. Yeah. You divide. We're finding current. So you divide the V over L. And you get I. And then
you're trying to use Ohm's law. Ohm's law only works for resistors.
V equals Li prime, right? So
that's true. V equals Li prime. But we want to find I, so you'll have to.
But we know the voltage and we know the.
Let's write them up here. V is equal to Li prime. That's true. But you want to go in the opposite way.
Right.
So what's the opposite way?
You take the integral of.
That's it. 1 over L times the integral from T naught to T of V of tau d tau plus your initial condition, which is I at T naught. So let's do that down here. It's 1 over L times, what's your initial condition? Where's your T naught? Where do you want to start looking at?
I mean, wouldn't it just be 0?
Mm-hmm. So 0 to T of your voltage, d tau, plus your current, plus your current at T equals 0. So let's fill it in. 1 over L is 1/6. And you'll take the integral of what? What's your voltage?
8 volts.
Mm-hmm. And what is your current at 0?
0.
Yeah. And for those of you listening to the video who are following along, he got that by looking at the original problem statement. So now it's just a matter of calculus. 1 over 6 times, let's see, if we're going to integrate 8 d tau, the 8 comes out of the integral sign. And so that gives us 8 over 6, which is 4/3. And the integral of tau is just tau. And we'll evaluate that from tau equals 0 to t. So that's going to be just 4/3 times t. And the units are going to be
amps.
amps. There's really only a limited number of things you can find here. You could find the current through each. Well, if you found the current through this guy, you can find the current through the 12 ohm the same way. Even faster, if you were asked to find the current through the 12 ohm, I'd say there's a total of 2t coming through it. Subtract from that the 4/3 t that goes on this side, and the rest has to be going through this side. And now you've got the current through every leg of this. You found the voltage across this part. You said it's 8 volts. You could do the same thing to find the voltage across this thing. It's this guy, L times the derivative of I. And you could find the voltage across here. And now you found the voltage across everything and the current through everything. Oh, if you wanted to find the voltage across this, the source, you'd add just by KVL the voltage across this plus the 8 volts across this, and that would have to be the voltage across the source. And now you've found everything. You've killed the problem. And all without having to memorize any clunky equations like current dividers and voltage dividers and things like that. All right, that was a lot of stuff. Do you have any questions for me?
None so far.
Excellent.
I think I'm understanding this a little better than I thought. So
do the collaborative problems and the solutions. They'll help a lot before you do the homework.